Actually, I would like to talk about some more general result that just got published. They got published a few weeks ago. So these are the titles. You can look on the internet for the published papers. So the first one, you got published last year in Geometry and Topology, Topological Rigidity, and H1 negative involutions on Tori. H1 negative means that the action of the involution is negative identity in the first homology. Just purely topological, not smooth involutions. This is joint work with my co-authors, Frank Connolly and Jim Davis. And the second paper is a generalization, which I would like to talk about today, where instead of the torus, you can go to the universal color, which is Euclidean space. And that's a contractible manifold. And so you can lift the action to an action of a crystallographic group. So more generally, look at actions on contractible manifolds where the singular set, where you have fixed points, is isolated or discrete. So in the example of the torus, the singular set is upstairs is the half integer lattice. You do reflection at half integer points. Actually, I would like to talk mainly about this. So for this one, the relation is, again, you have Rn, and inside here you have 1/2 integer lattice. And what you can do at the half integer lattice at any point is you can do reflection like this. And that gives you, and you can also do translation in the translation by Z. So reflection in half integer lattice, translation using the integer lattice. And this gives you an action of what's called a crystallographic group, or some people call it Bieberbach group. But maybe people don't call it Bieberbach group anymore because he was a Nazi.
So Bieberbach group is a group in which have no elements of finite order.
Oh, okay, maybe this is torsion free.
So crystallographic is just the factors or extensions of free abelian finite extension.
So maybe, maybe Bieberbach group is just the torsion-free crystallographic.
Yes.
So this is an example of you have a contractible manifold, Rn, and the action has a discrete singular set. This is where you have fixed points are in the half integer lattice. That's where you have reflection through each one of those points. So we wanted to generalize this phenomenon besides this simple example. We're going to look at other. First, we looked at Hadamard manifolds, Cartan-Hadamard manifolds. So these are simply connected Riemannian manifolds with non-positive sectional curvatures, and we generalized it to that situation. And actually, we went a little bit more general than that. So let me first, I have to tell you some language of all this and some history. You cannot see. I should not write anything here. So this will be the more general context of solving a problem in equivariant rigidity conjectures. Not just one special case, but more generally. These are transactions of American Mathematical Society. So you have a discrete group. And what we call family Russian, this is Semya. Family F in gamma is a collection of subgroups of gamma, which is closed under conjugation in gamma and taking subgroups. Meaning, if you have a subgroup in the family, then all of its subgroups are inside, and all of its conjugates are inside also. This is the meaning of technical meaning of family. Let me give you 5 examples of families. So there's kind of the trivial family, only the trivial subgroup. There's the family of finite subgroups. So the gamma we're interested in will be generally infinite countable. Then there is the family, this is kind of a little bit strange family. This means finite bicyclic. So that means it's of the form you have a group extension of a finite group by cyclic group. This cyclic group, if it's a finite cyclic group, it's just the same thing as saying H is finite, obviously. But this can be infinite cyclic also, in which case you say it is Z, then this will be automatically a semi-direct product. So this includes finite groups. Any finite group is finite by trivial cyclic, but more generally it contains finite by infinite cyclic also. So we allow a little bit of infiniteness. Then if we allow a little bit more of infiniteness, we have so-called virtually cyclic. And virtually means, virtually anything means there exists a subgroup with this property. So virtually cyclic means there exists a subgroup which is cyclic. It's actually, it's kind of like a joke. It actually looks like the opposite of this. There's a cyclic group inside. Normal, you can make it normal by intersecting with conjugates. There exists a cyclic group with finite index. So, as an example of a virtually cyclic is finite groups, because you can take a trivial group, right? You can take any finite group is virtually trivial. So you can make this a trivial group here, and then H would be finite. So this contains finite groups. So we have, this is contained in here, this is contained in here. This is a little bit harder to show, but it's a theorem that any virtually cyclic group is either finite or, so let me just comment.
Maybe in another direction. Inclusions in another direction.
Oh, sorry. So the virtually cyclics. So these are trichotomy, finite or finite semi-direct product cyclic. So that includes these, or finite by infinite dihedral. Infinite dihedral group. So this is isometry group of integers. So you can allow for basically a reflection. You can add that in.
How do we infinite dihedral group?
Let me write this. So infinite dihedral group. This is you can think of this as isometry group of the integers, and so it's z with the action of z mod 2 by negation is semi-direct product. This is one way of presenting it. Or you think about reflection in the integers through 0 and reflection through 1/2. These are generators. It will be freely generated. You think of it as a semi-direct product or a free product. So these are the extra types of groups. You have finite by infinite dihedral in here, but not in here. So this type allows for interesting two torsions, some reflections. And finally, there is the family of all cylinders. Now, usually in transformation groups, you want to look at, classically you have classifying spaces, so you have EG, BG, EG, all these types of things. EG, for a, say, topological group G, classifies all principal G bundles. So EG itself has to be a GCW complex or homotopy type of GCW complex and have a free action of G. It must be a free action. And then you divide by the action, you get BG. For certain purposes, like for like a crystallographic group, this will be too big. So for certain purposes, like for the example there, if you take the group, you take the group here to be this group. The action is by negation. This is a crystallographic group. B gamma is too big. I mean, you can construct it. E gamma is too big. But instead, you can just look at a Euclidean space, and it has an action of gamma. It's a proper action of gamma. It's not a free action because there are fixed points. But it's okay. If you are a little bit more relaxed, you can say, well, you will allow some fixed points where the stabilizers are finite. If you have a Lie group with the proper or topological group with the action with a proper action, maybe you want the stabilizers to be relatively compact. But just in the world of discrete groups, this means the same thing as finite stabilizers. So there, the stabilizers are all Z mod 2, different conjugacy classes of Z mod 2s. So you can talk about more general notion of classifying space. So I apologize for all these definitions. These are just necessary to talk about some conjectures. Gamma space X is a model that models E, F, gamma, or is a model for this. So the usual case is E gamma. It's a free gamma space. But now we allow for some stabilizers. But we allow only stabilizers in F. So if X has the gamma, this is just a technical condition, but gamma homotopy type of a gamma CW complex, it should not be too strange. And whenever you have a subgroup in your family, the fixed set should be non-empty. For every subgroup in your family, the fixed set here should be non-empty and contractible. Because in the usual case, E gamma is a contractible space. So we're having this kind of at each fixed set, this has to be contractible, in particular non-empty, for each one. And furthermore, if you are not in your family, then your fixed set must be empty. So that example here, related to our first paper, here Rn models E in gamma, with gamma equal to it's contractible, so Rn is contractible, and for the finite subgroups of this are order 2, and for each one of those you will find exactly one point where you do the reflection. That's contractible. And if you have a subgroup which is not trivial or of order 2, then the fixed set is empty. Another more general example is, do you guys know, Cartan-Hadamard manifold? Is Cartan-Hadamard? I guess I'll say it again. It's a Riemannian manifold, complete Riemannian manifold of sectional curvature less than or equal to 0. And the Cartan-Hadamard theorem says for these Riemannian manifolds, the exponential map is a diffeomorphism. So this has been a classical thing to look at, the geometry of such things. You look at transformation groups, proper actions by isometries, and the fixed set of any finite subgroup will be a totally geodesic subset. And that being totally geodesic, in particular, it is contractible. So this example here generalizes to more to. You cannot see below the point, right? It generalizes to something in differential geometry. Here are some facts. Autorial models for E, F, gamma. So the one we're mainly interested in is when the family is FIN, finite. But you can do this for anything. For E, F, gamma exist. This is due to Wolfgang Luke, a Bond, and a guy named Byron. They need some functorial models. Other fact, what does this do for you? What does it classify? This thing classifies. So E gamma classifies gamma CW complexes with free action. Those correspond to principal bundles. Here we can allow for some fixed points. So we control what kind of fixed points we have. And the third fact is that this is essentially unique, like E gamma is, that any two models for E of gamma are gamma homotopy equivalent. So just like with the usual E gamma, there's only one, basically there's only one E gamma up to gamma homotopy equivalence. Just like downstairs you have B gamma, there's only one B gamma up to homotopy equivalence. So this is just from universality, why this is unique up to homotopy equivalence. But say you are not a homotopy theorist, say that you're a geometric topologist, and for you, your equivalence relation is not really homotopy equivalence, but it's maybe homeomorphism. Then you could ask the question, this third fact here, is this unique up to homeomorphism or gamma homeomorphism? This is a question you can ask. So I would like to ask that in 1 second. I need to first tell you a little bit more. So as a geometric topologist, I'm also interested in manifolds, not just only CW complexes, but manifolds. So I need to give you a careful definition of manifold model, not just model, but manifold model. So suppose X is a topological manifold, not smooth, just only topological. Equipped with a gamma action. We say X is a manifold model for Ethan gamma, EF gamma. If, as a topological space, X models of gamma. And you need to say something about the manifoldness. And so for all isotropy groups, or this is the same thing as saying stabilizer. Isotropy groups H and K in F, and if the relationship between H and K is H is a subgroup of K. Given such a situation, we have the fixed set of H, and we have the fixed set of K. And we know from being a model, this is contractible, a contractible space, and this is a contractible space because both are in the family. But what happens, and of course, if H is contained in K, then the fixed set of K is contained, it's a Galois correspondence. The fixed set of K is contained in the fixed set of H. But how is it contained? Well, this is where we use the manifold part, that it must be a certain type of submanifold. Now, we do not have smooth manifolds here, we just have topological manifolds. And you can have strange topological submanifolds. Alexander Horn sphere is a topological submanifold of R3. It's not locally flat. So we want it to have to be locally flat. So is a locally flat submanifold of.
What is a locally flat?
Locally flat means for every point in here, there exists a neighborhood. So for every point in here, in xk, there is a neighborhood in here, such that intersection of this set in there looks like this is like a ball, and it looks like Euclidean space and Euclidean subspace. This is automatic for smooth submanifolds, but it's not automatic for topological submanifolds. So Alexander Horn sphere is bad. There's a Cantor set of bad points, but we force this. We do not require any type of tubular neighborhood or anything like that. That's too strong. We just want just locally flat.
Isotropy groups mean?
Isotropy is just a fancy way of saying stabilizer. It's just different people call it different things. And furthermore, this satisfies this was popular in the 1980s. The strong gap hypothesis. This was popular kind of in the 1980s, but then people forgot about it. So we got interested in it 30 years later. It's like Star Wars. Star Wars is coming back 30 years later. It satisfies a strong gap hypothesis if the dimension of this related to the dimension of this is, of course, this is less, but to be less than. Did I get that right? No. If the dimension of if is less than 1/2 the dimension. This will be convenient to avoid self-intersections. Okay, one more technical, it's a lot of definitions, I'm sorry. One more technical thing, and then I'll tell you some conjectures and some theorems. This is related to the gap hypothesis. We do not want any collapsing of the fixed sets onto each other when you compare one space to another. We want them to stay the same. So, a gamma map F from A to B. So this means that F of X gamma equals F of X gamma. This is gamma map. It's equivariant. This implies if gamma stabilizes X, then gamma also stabilizes F of X. So this is, a gamma map is, that's equivariant. It's isovariant if for all points, for all X in A, the stabilizer, so you have the stabilizer of F of X, and you have the stabilizer of X. So this is all gamma in gamma, such that X gamma equals X. This is the so-called stabilizer. If gamma stabilizes X for a gamma map, then gamma also stabilizes F of X. So you have this group contains this group. But we ask something stronger. Isovariant means actually that it does not get any bigger. It does not grow bigger. For example, if you take, you have R, N, and you have origin. And here you do reflection. So you have a Z mod 2 action is given by reflection through 0. Just like over there, that's what's happening. Okay, then you compare it to just one point space with the so your right action, Z mod 2, just trivial action. There is a mapping from Rn to the one point space, a constant map. This map is a gamma map, a Z mod 2 map. In fact, it's a Z mod 2 homotopy equivalence. You can take this point and bring it back here, everything is fine. However, this map here is not isovariant. Equivariant but not isovariant. Why? Well, if I take a point over here, not the origin, some other point, its stabilizer is a trivial group. But it's being mapped to a point with bigger stabilizer. Here the stabilizer became bigger. And that's not allowed, it should be equal. So this way, actually, if you look at more generally, Rn and Rm with such actions, then these two are not, these two are different because there's something called stratification. So here the stratum for the free points consists of Rn minus 0. Here it's Rm minus 0. And these two are different. They're not homotopy equivalent. This one, the free points are n minus 1 sphere, and here the free points are n minus 1 sphere. These are different. So these can be distinguished. They have the same equivariant type. They have the same equivariant type of a point, but they have different, more sharply, they have different isovariant types. So this is a whole family of examples, just simple. So isovariant is much stronger than equivariant. And why care? Well, homeomorphism, gamma homeomorphisms are isovariant. So the question of, is your homotopy equivalence a homeomorphism? It must have a necessary condition, which is being isovariant. It must preserve the isotropic groups, the stabilizers. Okay, so thank you for your patience. I will now tell you a conjecture, a few conjectures. So the classical Borel conjecture I think this is the modern language. So suppose X is a co-compact. Co-compact means X mod gamma is compact. Manifold model of E gamma. So this is the same thing as E trivial group gamma. Oh, let me see one more thing. So we talked about isovariant here. Let me we define the set S of gamma. This is called the structure set. It's something you can try to compute to be the set of gamma isovariant gamma homeomorphism classes of co-compact manifold models. So here the family we want is the finite, we allow for finite stabilizers. Proper actions. People call that a proper action for a discrete group.
Qayum, may I ask, E1 of gamma, this means the action, free action, or no?
Yes, that's right. That's right.
This is a free action. This
Yes.
is the stabilizer, that's right.
So Borel original conjectures, you look at actually X mod gamma. This is a compact manifold, and that will be a model for B gamma. And Borel says there's only one model up to homeomorphism. So in this language, I'm just trying to express it in this language, then in terms of this set, then this structure set, S of gamma, has only one element. And the Whitehead group of gamma is some technical thing. And when is this conjecture true? This is a theorem of Arthur Bartels in Germany. I think now he's in Münster. And Wolfgang Luke. I forget, maybe this is published in Annals of Mathematics. This conjecture is true when, for certain gamma, and gamma is what's called CAT 0, and the dimension of X is greater than 4. So T stands for Toponogov. If you've heard of Toponogov metric geometry. This is Alexandrov, and this is, I think, Cartan. And the that's cat space. Cat 0 means that in your metric space, you have a geodesic metric space, geodesically complete metric space, meaning you have a metric space and you have a notion of paths, length of paths, and that the distance between any 2 points is given by a path of minimal length. You can talk about, for example, a tree. You can put a simplicial metric topology on a tree, that's cat 0. It does not have to be a manifold. So there, if you have 3 points in your cat 0 space, and you join them by geodesic segments, then there exists a triangle with here for cat 0, it's in flat space, so Euclidean plane. So this is your cat 0 space. With the same lengths. And furthermore, so if I take, I should probably use color here. If I use the arc length parameterization, and I take a point here, I take the corresponding point here, and look at some point here, look at the corresponding point here, and I draw the chord and the chord here. This chord length should be less than or equal. This chord length should be less than or equal to here. So this gives you, you could have like a hyperbolic triangle. That's okay, but you cannot have a spherical triangle. So this can be more small. These angles can be smaller than here, but cannot be bigger than this. So it gives you an upper bound kind of on the curvature, in a sense, in a very metric geometry sense. So Riemannian manifolds of non-positive sectional curvature that are simply connected are cat 0. Cartan-Hadamard manifolds are cat-zero. But there exist some very strange cat-zero spaces. Michael Davis in 1985 constructed some strange contractible cat-zero manifolds that are not simply connected at infinity. They're very strange. So they're not homomorphic to Euclidean space. But they're contractible manifolds that are not homomorphic to Euclidean space. Very strange. But they are cat-zero. So more about this is written in the book of Brightson and Heffliger, Metric Spaces of Non-Positive Curvature. This is a very popular topic.
May I ask you one more about this conjecture? So, does it imply that X is a contractible manifold?
Yes.
Yes, this means that X is contractible and...
Because in the family, you will always have the trivial subgroup, because it's closed undertaking subgroups. So that means for the trivial subgroup, the fifth set for the trivial subgroup is everything.
And so for
In
this,
particular, it's contractible.
and for this reason, EG is in this notation is E1G.
Yes.
So the usual
Yes.
is EG is...
That's right, that's right.
And the statement is that S of gamma is the set of all gamma homomorphism classes of co-compact manifolds.
So there's only one there's only one manifold model for E gamma up to homomorphism. This is what that conjecture is saying.
It's compact, but it is compact and
Compact.
closed. It is
Quotient
closed.
is compact.
It is a closed compact manifold. Without boundary,
Yeah. Well, you look at the universal cover. So this is a statement about the universal cover, but you can divide and look at.
Well, I'm asking because if you take a manifold and multiply it by closed segment, and you consider the action which is.
So we don't allow for that because we don't allow for manifold with boundary. So these are all manifolds without boundary.
Should be closed.
Yeah. Well, not closed because they're actually non-compact. But closed usually means no boundary and
No,
compact.
but X by gamma is closed compact manifold. Is closed in that context.
Yes.
So this is essential.
Yes, that's right. That's right. X has no boundary. Yes. Okay, why did I say it in such a complicated way? Well, there's a much simpler way of saying the Borel conjecture. There's only one aspherical manifold with a given fundamental group. That's the short way of saying the Borel conjecture. Well, because I want to talk about an equivariant version of the Borel conjecture. And for that, I need all this language. So let me tell you that conjecture. Okay, this is due to it's due to Quinn originally, but he made a mistake. So this is based on Frank Quinn, 1986, International Congress of Mathematics address. But then my colleague Frank Connolly and his co-author Koźmiewski made a correct statement in 1990. So the conjecture states that, suppose that X see, you might say, why do you need this first sentence here? Because in the second sentence, you do not see X. It's not here. Gamma, there's no X. Why do you need this? Well, it just says it just guarantees that this is non-empty. So the first sentence, the only purpose is to make sure that S of gamma is non-empty. As soon as it's non-empty, it must be only 1 point. So same thing here. We have to guarantee your resistor model. Compact for infin gamma. And we're going to assume a little bit more. We're going to assume these strong gaps. These strong gaps. And then Frank Quinn tries to eliminate some complication by making an assumption of a group. Assume that gamma has no elements of order 2. So this will eliminate the infinite dihedral groups. Then S sub gamma, trying to calculate the set, it's not empty because of the first sentence, has only one element. And then there's a statement, technical statement from Connolly-Kozhniewski about the Whitehead group. There's an action of, there's an involution on the Whitehead group, on the topological Whitehead group. There's a thing due to Mark Steinberger, given by taking an H cobordism, equivariant, isovariant H cobordism, and turning it upside down. That's the involution. And you can look at the something called Tate cohomology, if that's, you need to assume that's 0. It's just a technical condition from K-theory. So again, you have, in particular, if gamma has no torsion, is torsion free, then you get the Borel conjecture. So it's a generalization of the Borel conjecture. This will allow for some stabilizers, finite stabilizers. And there's only one such manifold model up to gamma homeomorphism. So this is the conjecture from 30 years ago, and so we solve it. This is for this paper here, transactions. Got published 1 month ago. So this conjecture is called equivariant rigidity conjecture. Is true when gamma is the same thing over there. So gamma is cat 0. So for the group to be cat 0 means there is a complete finite dimensional cat 0 metric space on which gamma acts properly. That's what it means for the group. So it could be, for example, it's Cayley graph or anything. It doesn't matter. So the group to be cat 0. So when gamma is cat 0, and we have some technical things. Virtually torsion free. So for example, crystallographic groups are virtually torsion-free. They have a z to the n power inside the normal subgroup like that. But in general, we don't know this. The dimension of x greater than 4, because we use surgery theory. We use the Whitney trick. And one more condition, and this is related to the word that's titled discrete singular set. So this is just having isolated fixed points. So we found a way to say that in terms of only gamma. So the way to say it in terms of gamma is this. And condition star. The normalizer in gamma of any, the normalizer is finite for all finite non-trivial subgroup of gamma. Of course, the normalizer for a trivial group is everything, but it has to be non-trivial. And so we use so condition star so we use the result of Bartels and Luke. Actually, before this topological result, they had an algebraic result in terms of something called a Farrow-Jones conjecture. We used that algebraic result with assembly maps for our application.
Qayum, can you tell one more about cat zero groups? For instance, if you take crystallographic group, it has this cat zero property.
Yes.
So there is some way to look just on the group to say if it is cat zero or not.
No.
Or maybe there are some general.
Maybe. If you look at the Cayley graph, it's an interaction between the group and kind of how it acts by symmetries.
And how can you explain? Maybe there are some large classes of cat zero groups.
Okay. Yes. Okay. Hyperbolic groups. Oh, okay. Sorry. We don't know. We don't know if so. It's believed that hyperbolic groups, word hyperbolic groups, are cat zero, but it's not proven. There's some. So if you take a lattice in a isometry group of Cartan Hadamard manifold. So in the classical setting of non-positive sectional curvatures, and you have isometry group of that Riemannian manifold. That's a Lie group. You can look at a lattice or uniform lattice inside of it there. That's cat zero. Crystallographic groups is a special case where the Riemannian manifold just is flat. Is an example. You can look at isometries of hyperbolic space also.
And free groups or abelian groups?
Free groups. So cat zero groups are closed under taking subgroups, under free product.
So that is
This is fine. Free groups are fine.
And finite group, what about finite group?
Finite groups are cat zero because they act properly on a point.
And abelian group, no abelian if
yes, free abelian.
Free abelian, yes, these are all fine. These crystallographic groups.
And are fundamental groups of surfaces? What is another question?
Yes, because you have either the torus or surface genus 2 or higher that acts by us. It's a subgroup of isometries of hyperbolic plane. Yeah. So it's quite general, you know. If your group is coming from something geometric and that geometric thing has curvature less than or equal to 0, then you're okay. But I think it's unknown if all hyperbolic groups are. I think this is like a...
What's the fundamental group of Cartana-Tamara's group?
Yes, right.
Okay.
Right. Yes, yes. You know, there's some strange, like, you know,
I know.
monster groups or
Yes.
what do they call them? There's some strange groups that Gromov has come up with. They're not, you know, generically hyperbolic, but you don't know if they're cat zero. Okay. So I was saying this condition star is only a condition on the on gamma, but it's a nice condition. It's only talking about gamma. Because the conclusion is only in terms of gamma. But there's something called, from 1950s or so, called Smith theory, which talks about, I think, check cohomology and actions of P groups on certain types of spaces and looking at the fixed sets. This is from like Burrell's seminar around 1950s. It's very classical stuff. The Smith theory tells us that, so let me give you some notation here. So any more questions about this before I give you the outline of the proof?
Question about your example for n and fixed points, well, fixed submanifolds are points, and therefore strong gap hypothesis is not
Yes.
true. Or it's not valid.
When the fixed set are just points, then this is 0.
Yeah, and another is
And then this would be the dimension of x. So
it's not 0.
it's not, this is, yeah, these are only isotropic groups. So the only isotropic groups will be the maximal finite subgroups of gamma. It will turn out to be this. So,
Well, you said that they are ordered to H and K, so maybe they are equal.
no, I wanted to, so I mean, yeah, I mean,
Not equal. So this simply does not happen in the example.
in that example, in this example here, you can have, look at the partially ordered set of finite subgroups of this gamma. You have the trivial group, and then you have some groups of order 2.
Yeah.
This is it. There's no higher layers. So you have to do the comparison between trivial group and any one of these Z-mod 2s.
So
And
H is trivial and K is not.
Yes.
Oh.
The K is order 2.
No.
And there, it's true.
Yeah.
So you have a discrete singular set, the strong gap hypothesis holds because this is 0. We have a program to understand what if you allow for singularities that are not isolated. You have some semi-free action or some more complicated stratification, but then it gets very hard. So we just, actually this is kind of a baby case, just isolated fixed sets, isolated fixed points. But to talk more about what you're saying, you can look at the singular set. And this is just the set of all points such that the isotropic group stabilizer is not trivial. And O is X free. Those with trivial isotropy, trivial stabilizer. And something called Smith theory. In some kind of very advanced point set topology, Smith theory tells us that this condition star tells us that this is singular set is discrete. And we tried to avoid using a strong, like a heavy hammer, but we had to use this Veit-Thompson theorem about finite groups. There's some famous theorem about any finite group of odd order is solvable or something like this. There's some famous theorem from group theory that we had to use from algebra and also from topology, from Smith theory, to show this topological result. So we get discrete singular set. And this, to answer your question, this implies strong gaps. Because you have 0 dimension for the singular set. Okay, I will skip over some technicalities with algebraic K-theory, and maybe I'll give you a diagram, a kind of a flow chart or diagram of the steps. It takes many steps, many reductions to prove this. And this calculation of S sub gamma, this is an equivariant question, isovariant question. We want to reduce it to a question that is classical topology without any group action. But we cannot just simply take the quotient, because then you get some kind of, you like to say you get some kind of orbifold, but it's more general than an orbifold, because orbifolds have some condition about the action at a point has to be locally linear. We don't assume a locally linear action. So we have to be very careful. Okay, our goal is to compute, can you read that? S of gamma. So I assumed there exists, the S of gamma is non-empty. There exists X, manifold, co-compact manifold model. So what you can look at is, I will write this and I will then explain it. So this is the everything where you have n with the action of gamma proper, this thing automatically proper, is your manifold. X, you're given X, and you have an isovariant homotopy equivalence. So X can be very nice. It can be like a differential geometric, nice, very nice thing. Very nice, around each point you can have very nice link. And action is like by an orthogonal group. Very nice and nice. But N is like a fake version. It's like trying to be like X. It has isovariant homotopy equivalence. You take a point in here and look at its link. Well, first of all, you might not even be able to look at its link. It might not have a nice neighborhood, because the action of gamma on here is not smooth, you don't have a slice theorem, you don't have anything like that. You can talk about homotopy link. But anyway, even if you could talk about the link here, say the link here was a sphere and it is acting by reversing points. Then over here, it does not have to be that. It doesn't have to be exactly that. So there's some strange things that can happen. It can be homotopically that, but not homeomorphic or conjugate to that involution. So in the quotient, you could have a point, a singular point, and the link would be a real projective space. A real projective space. But over here, you take the quotient, you can have a fake projective space. There's some strange things that can happen. But these strange things are studied in surgery theory. So this set consists of all of these things up to the equivalence relation where you have M prime, you have another one of these, and then you have a gamma homeomorphism such that this homotopy commutes, gamma homotopy commutes. It's just like in the previous talk, the structure set. But this is equivariant version of the structure set. And also we require that not just homotopy equivalence, gamma homotopy equivalence, but isovariant, meaning the strata do not collapse. The isotropy, the stabilizers get mapped, get preserved. So first step is we build a map this way. So the map this way is simply forget about this. You have M. And M will be another, if X is a model, then M will be another model for E fin gamma. Because the criteria for being a model for E fin gamma is that the fixed sets are contractible for finite subgroups and are empty otherwise. But empty and contractible are invariant under homotopy equivalence. So this is a forgetful map. So we actually show that this is a bijection. That's the first step, meaning any model here, for any M that's a model, we can then show there exists an isovariant map to some X. So we're showing that this is bijection. So we're adding some more structure. Now, these things are just M with the gamma action. These things have M, gamma action, and this map. So we're adding more structure. Then we want to get rid of the gamma action. So we need to take a special type of quotient. Here, this is X bar is a compact manifold. I call it boundary manifold. Manifold with boundary. That's the boundary. And if you remove the boundary, this will be the same thing as the free part of the action. So you remove the singular points and divide by gamma. This will be some kind of open manifold. You just kind of remove all the singular points and you get some kind of, you get some cusps, you get some ends to your space. So we can then compactify, we can put a boundary onto that for a nice type of X. This mapping here, so this consists of all manifolds M bar with boundary, and there's a map of pairs to this pair, and this is a homotopy equivalence of pairs. So meaning a homotopy equivalence from here to here that takes the boundary to here by homotopy equivalence. There's no group action, just homotopy equivalence of pairs. And you can get such the map this way is given by going to the universal cover, to the gamma cover. This go up to x, then look at the universal cover of this. There's a gamma map between them. Those are free gamma spaces. Then you need to fill in the holes. So you might have, this may be something like there's some hole in here. Then it goes upstairs to some thing with some holes. Then you want to fill in the holes. And so you can just, the holes, each one of these holes is going to be a sphere in the nice X, in the nice model X. Over here, what you'll get is something like this, but you'll have homotopy spheres. But something called generalized Poincare conjecture says that any homotopy sphere is homeomorphic to a sphere. So then over with the n, when you look at the universal cover here, you get actual spheres, and then what you can do is take the cone and fill these cones in here, and also when you do this over here, and you take the cone of the action also. That will give you an isovariant map. So this map here is given by going to universal cover and taking cones. But now actually we proved that it's a bijection. We proved that it's a bijection. So this means I can reverse the process. So if I have such data, this type of thing, with isovariant homotopy equivalence, what I can do is remove the singularities from here and from here. So actually, first I need to know, okay, so the singularities here must be discrete. That uses the Smith theory. Then I can remove them. And then the action of gamma on that complement is free. And I can divide by the action. And I'll get some kind of non-compact manifold. But I need actually, for these, I need compact manifold to boundary. Compact manifold to boundary. So I have some open manifold. Maybe it looks like this. Where I divide after removing the singular set, and I want to compactify it. And this is a problem studied by Siebenmann in the 1965. It was his PhD thesis. When can you, on a topological or smooth or PL manifold, when can you put a boundary on this? And he has some necessary conditions. There's some kind of tameness condition. It's a homotopical condition. And once you have that tameness condition, even with that tameness condition, the tameness condition says this, that there is a deformation retraction of this space to a compact set, to a compact subset. This is equivalent to being dominated by a compact space. But even that is not enough. There is still an obstruction in K theory. So an obstruction in the projective class group, the fundamental group of the end. And the fundamental group of the end will be the same thing as the stabilizer. That'll be some finite group. So this projective class group of finite groups can be not zero. For example, the quaternion group of order 8, the projective class group is not zero. So you can have some strange things. So we get worried. Can you actually go this way? But we do some tricks. We do a trick called the Eilenberg swindle. I'm just telling you some details about this. We use something called Eilenberg swindle. I don't have time to talk about it. It's some kind of infinite trick that lets us deal with the situation. And lets us actually put a boundary onto this and get a compact manifold. a compact manifold with boundary. So there's some classical topology, manifold topology. But now this is very good because now we have reduced the problem to something without gamma. It's a question about compact manifolds with boundary. So calculate this. Okay, let me just give you a quick outline of this. The rest is just classical surgery theory. Well, classical surgery theory plus some algebraic surgery and some assembly maps. So it's basically algebra. What's remaining? Okay, we're going to calculate that. Okay. This H means homotopy equivalence. There's something called the algebraic structure group of Andrew Rudnitsky. It's an actual group. This over there is a set. This is a group. So this map from this algebraic is a map, and it's a bijection. This is using the Rudnitsky total surgery obstruction, the relative form of it. Where you need dimension, where n is the dimension of x and has to be greater than 4. Okay, now it becomes some kind of, whatever this is some kind of functor, covariant functor on pairs of spaces. Now it becomes algebraic topology. So now we can, there's some technical thing about K-theory decorations. We can get rid of the decorations by some tricks, isomorphism of groups, abelian groups, using something called Rothenberg sequence. So this is using a relative form. Relative Rothenberg. This is all classical stuff. And then, how do you calculate this? We're trying to show this is only one point, meaning as a group that it's a zero group. Okay. There's some type of equivariant topology theory due to Jim Davis and Wolfgang Luck from 1998. It's more general than Bourdon. Well, it's a type of Bourdon homology. It's something like that, but it has values in spectra. So you can look at the map from X going to a point. This is a gamma map. And you can look at the relative term in the long exact sequence for a pair. And you look at it with some coefficients. The coefficients are in L theory. Whatever this is. L theory is some kind of something to do with quadratic forms, basically. K theory has something to do with projective modules. L theory has something to do with quadratic forms over those projective modules and automorphisms of those quadratic forms. The quadratic form arises from looking at the intersection pairing in the middle dimension of an even dimensional manifold. Anyway, you get some kind of spectrum here, but actually you get a different spectrum for each fixed point. So this is it's some fancy thing. It's a co-sheaf of coefficients. So this is a isomorphism here. We do this by identifying assembly maps. An assembly map is a way to, if you have a functor of from spaces to spectra, or spaces to abelian groups, which does not satisfy excision, but you want it to satisfy excision, then you can make an approximation to that functor on the left, a left approximation, which does satisfy excision. That's called an assembly map. K theory and L theory do not satisfy excision, but you can do left excisive approximations. Okay, and this thing here is a type of generalized Berdan homology. So Berdan homology takes into account the different, gives you a different coefficient group for a different fixed set using the stabilizer, where this thing here is a functor. So Berdan introduced something called the orbit category. This consists of homogeneous spaces, G mod H or gamma mod H. So this orbit category, the morphisms are gamma maps. So from this orbit category, you go to spectra in the sense of algebraic topology. Spectra are the things that control generalized homology theories. Okay, so now this is forgetting about surgery. Now this is a question about some relative homology group. And this is where we do some cool tricks. So we do first that this group is equal to I will write these classified, there's boring Skuchny classified spaces that were in the beginning. They're coming here. So a model for E all is just a point. Everything is fixing that one point. The same thing as this point here. And a model for E fin gamma is X. Because why? Because of these biases. Okay. So I just changed the name. I don't do anything interesting. I just changed the name here. And so now I'm going from this family to the bigger family all, from finite subgroups to all subgroups. I'm seeing what is the information what's the difference in the information here and here with these coefficients. And then there is some kind of zigzag of isomorphisms to show that this is the same thing as changing to another pair of families. So the ones I was talking about before, finite bicyclic, remember that we had trivial family contained in finite, contained in finite bicyclic, contained in virtually cyclic, contained in all. So now I make the family bigger here, and then here I make this family smaller. Like this. So now you see there's a big gap between finite and all. This is too big. So what we do is we use some tricks and we make that gap smaller to do a calculation. Now we have a small gap. You have a smaller difference between, so here you have finite and all, and we replace it with this to this. It's smaller, it's more tight. Okay, and then we show this is 0. Because no two torsion in gamma. There's some specific properties of this functor that as soon as you have no two torsion, then there is no, then what is this? And what is this? This is this family. This family is same thing as this family plus finite by infinite dihedral. These are the extra things here. So if you have no two torsion, then you do not have any of these. And then these two are equal. Because of no two torsion. So that means this relative homology group is 0. This is just identity map. So that's the outline of the proof. There's many transformations that happen. And let me make one more comment, if I may. What if you have some two torsion, some elements of order 2? We actually give an answer, and they're, let me say, the last thing I write. If your cat 0 gamma has two torsion and satisfies star, then this relative group is isomorphic to S of gamma, is isomorphic to something. We can calculate this. And this is a direct sum of some groups with strange names, UNIL, unitary nilpotent groups. And this direct sum is taken over all these type of groups. So these are the maximal, infinite, dihedral. Subgroups. In gamma, up to conjugacy classes. So for the example of, here you have two torsion. There's lots of two torsion. But the number of conjugacy classes is 2 to the power n. You can show this. It's like you go to the torus and there are 2 to the power n fixed points. So this is a finite direct sum. There's 2 to the n conjugacy classes. What is this group? This group is calculated by Sylvain Capel in the 1970s. And remember in the first talk I told you half the time everything is okay and other half the time things are bad, actually very, very bad. Same thing here. This group, UNIL, is 0, 0, that's half the time it's good. If n congruent to 0 modulo 4 or 1. And then when n is congruent to 2 modulo 4, you have infinite direct sum of z mod 2s. This is basically some type of Kerrer-Arf invariant. But instead of over the field of 2 elements, it's over the function field, over some function field with transcendence degree 1. And then here, you have something called quadratic linking form. And there you get answers. So some more advanced quadratic form theory. You get something like that. So it's when it is either it's 0 and you're happy, or it's infinite. So that's a complete calculation, even if you have elements of order 2. So in particular, for the case of, in particular, as this is such a 2 to the n copies of u.
Qayum, what is n in the description of union?
N is the dimension of x. X is a co-compact manifold model for E from gamma, so n is the dimension of x. So that's the answer in the first paper, where we allow for some 2 torsion. But if you have no 2 torsion, then you get an answer of 0. So 2 torsion is really the problem. Thank you for your attention.
Thank you very much. Any questions?
So if you have not 2 torsion, that you have not the element of Borel conjecture, yeah?
Yes.
Prove
We
that
have
the
to.
Borel conjecture is not true, yeah? If you-
Right. This conjecture B assumes no elements of order 2. You might say, okay, that's kind of a coward's approach. Why not make a stronger conjecture, eliminate this, and give an answer like this? The problem is, because we have just discrete singular set, it's kind of easy to describe, for each conjugacy class, for each orbit of singular point, you have one direct sum. But if you have some more complicated stratification, then they're fitting together in some weird ways, and it's not going to be a direct sum. It will be some co-limit of something or another, something very complicated. And Quinn did not have any language to describe this type of co-limit or some type of arrangement of information when you have elements of order 2. We also have kind of a guess. Privately, we have a guess, but we are not sure. So this is why we take it in some small steps. We first do the case of a discrete singular set, then we will talk about, we were doing research where then maybe you have, just a it's called semi-free action. Like this. And then you have some, tubular neighborhood, and then you can work around the tubular neighborhood. Maybe you get homology of the base with coefficients twisted in something with the fiber or something. It gets very, but then if you have stratification, it gets too complicated. So we are just trying to understand what's going on.
Excuse me, what do you mean VC group?
Yes, this is from before. This is the virtually cyclic. Virtually cyclic. So these were the groups.
Finite bicyclic, is it a subgroup of virtually cyclic? I think no.
So VC. And there's a theorem that says that it's either finite or finite F, or finite semi-direct product Z, which is finite by infinite cyclic, or finite by infinite dihedral. So the difference between VC and FBC, so these two are just FBC, finite bicyclic.
What is finite bicyclic?
This is only just these two. It is of the form,
I meant another thing.
Even
Okay.
the other way, yeah. But that's virtually cyclic. Yeah.
I meant.
So when you do not have to worry about these infinite dihedral groups, then this index set here is empty. So it's an empty direct sum that's 0.
Any other questions? No? So let us thank Qayum again. Thank you very much.